Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk about how the notion of tensor products interacts with the notion of duality in the theory of vector spaces. Okay, so the first thing I want to talk about is this notion called contraction. Okay, so let's set up the notation that we need first. V here is some finite dimensional vector space over our field F. And so since it's finite dimensional, we can consider a basis, say, V1 up to Vn. We're going to look at the dual space. So let's just remember what that is. This is just the space of all linear maps from V to F. Okay, so these are F linear maps from V to F. Now, one of the things that we know from the theory of vector spaces, linear algebra, is that this has a dual basis. And the way I'll write the dual basis, following conventions of physicists and differential geometers, is V upper 1 up to V upper n. Okay, so let's remind ourselves, what does it mean to be a dual basis? Okay, so let's suppose we have Vi, one of these dual basis vectors, and we have one of the original basis vectors, Vj. Okay, since this is a vector inside V, okay, you can apply this Vi, which is inside here, to get you some sort of a scalar in F. Okay, so what's Vi of Vj? Well, this is going to be, since it's a dual basis, is by definition equal to the Kronecker delta, delta ij. So it's 0 if I is different from j, and 1 if I equals j. And that's the notion of a dual basis. Okay, so if you have n vectors, which Vi, V1 up to Vn, which satisfy this equation here, then it will give you a basis for this dual space, and it's called the dual basis. Okay, so what I want to do is to look at the tensor product of V star with V, okay? And I claim that there's a very special map called a contraction map. And this is a linear map from V star tensor V to F. And I'll denote epsilon subscript V. It of course depends on V, and epsilon because it's a type of evaluation. Okay, so to define this map, I just need to tell you what it does on elementary tensors. Suppose you have an elementary tensor here, V star tensor V. What is the scalar that it maps to? Okay, so of course, just as we did here, okay, we can substitute V into this linear functional V star and evaluate it to get a scalar. Okay, so that's why it's called, it's also a type of evaluation map, and I've used the letter epsilon. Okay, so that's great. This is a contraction map, and it's a very, very important map when you study tensor products. Okay, and especially if you mix it with the notion of duality. Okay, so let me just prove for you roughly this proposition here. Okay, we're just constructing a linear map showing that this exists. This is a well-defined linear map, and as usual, to define maps out of a tensor product, you just have to check the universal property. Okay, in other words, if we look at the corresponding map from V star V to F, which maps the pair V star comma V to V star of V, okay, then this is bilinear in V star and V. Okay, that's all we need to check. Once it does that, then this linear map exists, and it has this precise property which defines it for you. Okay, so let's see why that's true. Okay, so we won't go through the complete check, but basically, why is it true? Let's check linearity in V first. Okay, so now we've fixed the V star, but V star is a linear map from V to F, so that means that it's going to be linear in this V. Okay, the next thing you have to do is to check that it's linear in the V star. Okay, so let me just check firstly that it preserves addition. Okay, if you fix the V, it preserves addition. So let's see what happens there. Okay, so let's suppose we look at, instead of just V star, but V star plus W star. So we now have two elements inside this V star. Okay, and we look at this pair here, and want to see where does it get mapped to. So where does it get mapped to? It gets mapped to V star plus W star, this linear functional, and then you evaluate it at V. Okay, but this object here, well, how do you define the sum of these two? Remember, what is the sum inside this dual space? Okay, it's just pointwise addition. So this is just V star of V plus W star of V. Okay, and of course, what you find out is that, well, this is where V star comma V gets mapped to, and this term here is where W star V gets mapped to. Okay, so it's also true that the V star, so let's just remove this for the moment. Okay, we don't need that. So the point is that V star comma V gets mapped to this one, and w star comma v gets mapped to this one here. So of course the sum, okay, where it gets mapped to gets mapped to the images of these two, and you take the sum of them. Okay, so that's to check that this map preserves addition in this first variable, and you can similarly check that it preserves scalar multiplication in that first variable too. Okay, so that's great. And what I want to do is now to show you some examples of this contraction map. Okay, so let's suppose the v and the v star have a very special form. Okay, so v you can always write down as a linear combination of the basis elements. So let's suppose that v equals the sum of alpha I. So we'll use the usual Einstein summation notation: sum of alpha upper I, v lower I, and this v star is equal to the sum of beta lower I, v upper I. Maybe I should use j here. Okay, so now let's have a look and see what happens when we do what's epsilon, this big V, of v star v. Okay, so we just basically evaluate this vector, this linear functional rather, at this vector. So we're going to look at the direct sum of beta j v upper j. Okay, here's a linear functional. It's a linear combination of these linear functionals at this vector here, sum of alpha I v I. Okay, so this should be a tensor rather, sorry. Okay, so epsilon v, v star tensor v. Okay, that elementary tensor. Okay, so let's see how this works. Okay, so what do we need to do? Okay, we just need to evaluate this linear functional at this vector here. And remember, this is linear in each of these variables. So I can pull out the sum, I and j, both of them in fact, and pull out these scalars as well. Okay, so that's linearity in this variable and linearity in this variable. So you have beta j alpha I, and then you just evaluate vj at vi. Okay, and what is this equal to? So in this case, it's just delta ji. So most of the time it's 0, except when I equals j. So that means that the only times that you get something non-zero is when I equals j. So we can just sum over I and look only at those j's for which j equals I. So that's the sum of beta I alpha I. So if you look at the contraction of this vector in the dual space with this vector here, okay, it's got a very, very nice form. Of course, it has to be a function of these coefficients here and these coefficients in here. And what is this? It's just the sum of beta I alpha I, okay, this product here. And one thing that you should note from this expression here is it looks a lot like the dot product, okay? This is very, very similar to what you see with the dot product, except for in the usual Euclidean dot product, what you'll find is that you're working with the same space. It's not a space and it's dual space. So we looked at the contraction map from v star tensor v to f, and what I want to show now is there's actually a partial converse to this result. Okay, so let me show you how this works through the notion of pairings, and that's involved in this proposition definition here. So now what we're going to do is we're going to consider two vector spaces over f, x and y here. And what's the notion of a pairing on that? Okay, so this is something that's just new terminology for something we've seen before. Okay, it's just going to be a bilinear map from x cross y to f. Okay, so the example that we saw before was v star cross v. We can evaluate a linear functional at the vector, so that gives us a pairing in that way. Of course, since it's a bilinear map, this is equivalent information to giving a linear map from the tensor product x tensor y to f. Okay, so if this is the bilinear map phi bar will be the linear map on the tensor product. Okay, so now I want to look at this setup where we have this pairing, and I want to relate it to the notion of duality that we had before. Okay, so what I claim is that if you have this setup here, and this is the proposition part of this proposition definition, you get a linear map from x to the dual of y. Okay, so this is what happens when you have this pairing. Okay, so let's see how that works. So how does this map work here? How do we define it? So let's suppose you have x as a vector inside this big X. Okay, I need to give you an element of y star, so a linear functional on y. So it should map y to some scalar. Okay, so what scalar does it map to? Y maps to what? Okay, so what I'm going to do is I'm going to involve the x and the y, and I'm just going to map this with phi of xy. Phi of xy is of course some sort of a scalar. And remember, this is a bilinear map. So that means that if you fix this x, of course, it's going to be linear in this y. So that's why you get a linear map from y to f. So in other words, an element of the dual space of y here. Okay. So this gives you a map from here to here, and it's quite easy to check that that's linear as well. Okay. So that's rather nice. That now, conversely, if you have some sort of a pairing, okay, it doesn't necessarily have to be essentially of the form v star tensor v gets contracted to f, okay, but what you do is you see that this term here is related to the dual, okay, using this setup here. So x at least maps to the dual here, okay. So this is not equal to the dual of y, okay, but it does map to the dual of y at least. Okay, so the special case that often occurs in mathematics that's very interesting is when this map is actually an isomorphism. Okay, this phi tilde is an isomorphism. So when that's an isomorphism, phi tilde is an isomorphism, we'll say that the corresponding pairing, either as a bilinear map like this or as a linear map from the tensor product, that is non-degenerate. Okay, so let me give you a little example of that so you can see what goes on. And it's really not such a difficult concept after all. Okay, so our favorite bilinear pairing, this first one we ever learned is of course the dot product. So let's suppose x and y are both equal to Rn, okay, and we'll think of Rn as usual as column vectors, n tuples where we write it as a column. Okay, then phi is going to be the dot product. So let's just see how phi works out to be. So phi of x, y is just x dot y, okay, and the best way to write that out is of course you just do x transpose y. Okay, so this is a 1 by n matrix. It's a row vector. This is a column vector. You multiply them, you get a 1 by 1 matrix, so essentially a scalar. Okay, so what does this phi tilde do? Okay, so let's look at this phi tilde. Phi tilde should go from this x, which is Rn, gets mapped to Rn, the dual of that. Okay, so how does that work? So what the image of x is, so we'll pick an x inside here, and let's see where it ends up. What you want to do is you fix this x here, so in other words this x here, you fix this x, and you look at this as a function of y. So you fix that x now, and you want to think of this as a function of y. Okay, so what is this as a function of y? So basically you're just left multiplying y by x transpose. Okay, so remember this is just a row vector, and as a row vector, since it's a 1 by n matrix, okay, it eats up column vectors, things inside Rn, and spits out a length 1 vector, so in other words a scalar. So in other words it's an element of Rn dual. So in this case here, this phi tilde is quite simple to say what it is. It's just x transpose. Okay, so it's very, very nice what this phi tilde does in this case. Okay, it takes a column vector and it just transposes it so it becomes a row vector. Okay, and row vectors are naturally elements of the dual space of Rn if we think of Rn as column vectors. Okay, so that's one way to distinguish Rn from its dual space. If this is column vectors, then the dual is row vectors. Okay, and this gives you the isomorphism between them, and one way to get it is just to use a pairing, and the pairing is the natural one we have here, the dot product. Okay, and this is also related to the fact that we see something that looks like the dot product when we looked at the contraction map before. Okay, so I want to look at a more sophisticated version of this, okay, and this is a very simple example of the Hom tensor adjunction formula, okay. So it looks rather nasty when you write it out like that, okay. So we have in this Hom tensor adjunction formula an isomorphism between vector spaces. Okay, so let's look at the two vector spaces. You have this vector space here, okay, so x tensor y is a vector space and f is a vector space, so you can look at the vector space of linear maps from x tensor y to f. Okay, so here I'm going to write down the dual. When you write down the Hom tensor adjunction, you usually write this out as a Hom. So this is just a linear maps from y to f, Hom y f. That's a vector space. So you can look at the vector space of linear maps from x to this dual, x to y star. Okay, and I claim that these are isomorphic as vector spaces even. Okay, so let's see what the isomorphism is at least. So let's suppose you have a phi here. Okay, so that means you've got something like this, or phi bar here rather. You have this linear map from here to here, so there's an associated bilinear map phi from x cross y to f. And using this sort of idea here, you get a linear map from x to y star, x to y star. So this phi tilde is the corresponding map here. And it turns out that actually, okay, when you look at this, okay, what you'll find is that, yeah, you get this isomorphism. Okay, so it's really interesting that this is not only bijective, but also it preserves the vector space structure on both sides. Okay, so if you carry out this construction for each and every element here, okay, you'll get this isomorphism of vector spaces. Okay, and that also gives us actually a different way of looking at the notion of degenerate pairings. Okay, degenerate pairing gives you a case where this is an isomorphism. And since you have this isomorphism, this Hom tensor adjunction, okay, there's basically a 1-1 correspondence, okay, between isomorphisms from X to Y star and non-degenerate pairings. Okay, so when you're looking at this isomorphisms to X and Y star, okay, that corresponds essentially to the contraction that we looked at, except for you have to use this identification to write it out as in the form Y star tensor Y, okay, if you use this identification here, okay. And then they correspond to the non-degenerate pairings, okay. And so the other pairings give you the case where just X maps to Y star, but it's not an isomorphism. One very natural question we have is there a relationship between the dual of X tensor Y and the tensor product of the dual of X and the dual of Y? And the answer is that there's actually a very strong relationship between them, okay? So firstly, there's a natural map from X star tensor Y star to X tensor Y star, okay? So let's see how that works, okay? So what does it mean to map to this dual here? Remember, one of the things that we saw is that to map to this dual, all we need to do is to get a pairing, okay? A pairing from this with this here. So let's construct that pairing. So we're going to start with X star tensor Y star. And to get a pairing, we need the tensor product of this with the thing you want to pair it with, X tensor Y. And you want to have a linear map from here to the field. Okay, so let's see how that works. Well, remember what happens here. The tensor product is associative. So you can remove the bracket and it doesn't matter how you bracket it, you'll get the same result. The next thing is it's also commutative, okay? So it's a symmetric, okay? So you can actually swap these two around, drop all the brackets and swap these two around. So there's a natural map to X dual tensor X tensor Y dual tensor Y. Okay? So why have I done that? Well, X dual tensor X, there's a contraction map, epsilon X, and Y dual tensor Y, there's a contraction map there, epsilon Y. Okay, so X star tensor X, you can evaluate a linear functional at any X to give you something which is a scalar in F. And you also have an evaluation or contraction map on Y. So this Y star tensor Y maps to F here. Okay, so we're using the functoriality now of the tensor product. And F, tensor F, of course, well, this is like the identity. So this is naturally isomorphic to F. Okay. So we see from this, okay, this very simple argument, just using simple associativity properties and symmetry properties of the tensor product, functoriality, and also this unit property here, that we get a pairing of X star tensor Y star, X dual tensor Y dual with X tensor Y. So that means that you're going to map from here to the dual of this. So that's this one here, okay? Okay, so let's see. So we've constructed the natural linear map in part A. Let's see what happens with part B. Okay, let's try to understand what this does. Okay, so I've defined what the iota does, so I just need to unravel this definition. And I claim if you unravel the definition, you get the following rather nice formula. Okay, so what's iota of X star tensor Y star? So we've applied iota to this elementary tensor here. You land over here. Okay, so that means it's a linear functional on X tensor Y. So if you input an elementary tensor, okay, it should spit out a scalar. What's that scalar? It's got to be a function of X star, Y star, X and Y. Okay, well, the natural thing to do is, well, how can you get scalars? You can evaluate X star at X to get a scalar and Y star at Y to get a scalar. And how should you put them together? Well, it turns out the way to put them together is just to multiply these two. Okay, so let's see how that works. Okay, so remember how this thing works here. Okay, so the relationship between a pairing and a map here. Okay, so how does that work here? Okay, so let's start. You've got X star tensor Y star inside here. Okay, and then you use this pairing. Okay, you've got this pairing, and the corresponding linear map is, well, you fix this element inside here, and you substitute things inside here. It's a function of this variable. So you've got x star tensor y star, and you've got x tensor y inside here. So here's x star tensor y star, that's inside here, and you feed in an x tensor y inside here, like that. And see where this goes, and that will tell you where this left-hand side ends up. Okay, so you can swap these around. That's what we did here. Okay, and then you apply epsilon x, which means you get x star of x. So you've got x star of x here, tensor, and over here, when you do the other contraction, you get y star of y. And then you have to look at the isomorphism here, and the isomorphism here is just the product. So that gives you part B of this proposition here. Okay, that's great. So you can relate these two, and of course the natural question you really want to know is, well, when is this an isomorphism? Is it an isomorphism ever, or are there nice conditions when it is an isomorphism? And the wonderful thing is that when x and y are finite dimensional, in fact, then this iota is an isomorphism. So this is another way you can think of the dual of x tensor y. Okay, and before proving this, okay, I want to talk about the following corollary, which is one way to think about it. Okay, so what is this dual space here? Okay, this dual space linear maps from x tensor y to the field f. Okay, so they're basically just bilinear maps from x cross y to f. So you want to look at this space here is the same as looking at the vector space of bilinear maps from x cross y to f. And what this is saying is, well, you can write it out as this tensor product, x dual tensor y dual. Okay, you can think of it in terms of linear functionals on x and linear functionals on y. Okay, so this is a very nice way to re-characterize bilinear maps on this product of vector spaces. Okay, to at least bilinear maps from this product to f. Okay, so let's see why this is true. Okay, and the way we'll do it is as follows. Okay, so we have a map like this. And the first thing to realize is that, well, what is the dimension of this? Okay, so the first thing to note, so for part C, okay, so the first thing to note is that the dimension of both sides, dimension of the left-hand side equals, well, it's a tensor product, so it's the dimension of this times the dimension of that. And the dimension of x dual is, of course, the same as the dimension of x. And the dimension of y dual is the same as the dimension of y. So this is dimension of x times the dimension of y. And then if they're isomorphic, right, these should have the same dimension. So let's just check that. Okay, so when we look at this, well, this has dimension, the tensor product, dimension of x times the dimension of y. And when you take the dual, it doesn't change the dimension. So this is just the dimension of the right-hand side. Okay, so that's good. And now you just have to check that this is either injective or surjective. Okay, so let me just show you a direct way to do it. Okay, so this is a good thing to realize to help you appreciate that these might be isomorphic. So to show it's an actual isomorphism, I guess you can show it's either surjective or injective. So we'll consider bases, say x lower I for x and y lower j for y, and dual bases x upper I and y upper j. So what I want to do now is I want to show you how iota maps a basis here to a basis here. And once I've shown that, then we're done. Okay? So how do I show that it maps a basis here to a basis here? So we get a basis. Well, to get a basis of this, remember, you just take tensor products of bases. Okay? So what does that mean? Okay, so you have a basis xi tensor y j of x dual tensor y dual. And this is all I have to do is to show that it's a basis of this dual space, is to show that it's actually dual to a basis here. Dual to the following basis, xi tensor, or xr tensor y s. So let's just check this thing, that this, so I guess it's not dual at the moment, but when you apply iota, you land in here. So this on applying iota. So let's have a look at iota of xi tensor yj evaluated xr tensor ys. Okay, that's what we want to do, and we want to check that this iota of this basis here, when you map by iota, it gives you a basis here because it's just a dual basis to the this basis xr tensor ys of x tensor y. Okay, that's the goal. But what is this equal to? Now we can use part B to work out what it is. I just evaluate this linear function x upper I at xr. Of course, that's the Kronecker delta delta IR. And then I multiply it with y star y, so I evaluate yj at ys. And that's, of course, just the Kronecker delta, because these are also dual bases, so that's delta of js. So basically, when is this equal to 1? The only time it's equal to 1 is going to be 0 all the time except when it's 1, which is 1 times 1. That means that I equals r and j equals s. Okay? So we see that the set of these vectors here, so the image of this basis here, okay, is a dual basis to the basis of these, and hence a basis of this as well. So since it maps bases to bases, okay, this is indeed a isomorphism of vector spaces in the case where x and y are finite dimensional. And this gives us a lovely characterization of the space of bilinear maps from x, y to f. Okay, the space of pairings from x and y to f. Okay, is given by this tensor product x star tensor y star. I hope you enjoyed this adventure in pure mathematics.